So let's learn the basics of TensorFlow while solving a real-world problem. If you recall our MNIST dataset that we have discussed in the dimensionality reduction chapter, right? What does it? So we have a nice video on what is MNIST dataset and things like that. So if you have forgotten some of what an MNIST dataset is all about, please go back to the chapter of dimensionality reduction where we have discussed in a lot of detail. In a nutshell, in MNIST dataset, you are given handwritten digits of 28 pixels by 28 pixels. Like somebody gives you this, and it will predict whether, you have 10 classes, whether this image belongs to class 1, class 2, class 3, or up to class 9. So you have a 10 class classification where the input data, because you have an image of 28 pixels by 28 pixels, we convert this into a vector of size 784 dimensions. Okay, and this is basically a vector where you have real values, okay, between 0 and 1. So given a 784 dimensional input, what we have here, and this input is basically the vector representation of this image, right? And we have a 10 class classification that we have to solve. So if you've forgotten some of the details about MNIST, please revisit the chapter of dimensionality reduction where we've discussed this in a lot of detail. Okay, so coming back to TensorFlow. First I want to get the data into TensorFlow, right? Thankfully, MNIST data is already available in tensorflow.examples.tutorials.mnist. So TensorFlow also gives you a lot of tutorials using MNIST data because it's extremely simple. It's very easy to understand TensorFlow using this example, and we are doing the same thing here. So I'm importing it. So from this, I'm importing the input data, and I'm calling this whole data as MNIST. MNIST is input data.read datasets, and I'm saying get me the MNIST data with a one-hot encoding of the data. So now it will take a few minutes to extract all the data for you because TensorFlow comes inbuilt with all this data set. So it's getting all of this zipped data into the variable MNIST here. Okay. Now I'm just importing NumPy, all of that stuff. So the data set. So there are some properties of the data set here. Let's go through it. So if I say MNIST.train.images.shape, okay, so what it tells me is I have in the training data, I have 55,000 images where each image has 784 pixels. This is nothing but 28 by 28, as we have seen with MNIST in general, right? So you have 55,000 training points, and similarly you have MNIST.test.labels.shape, and you have 10,000 test data points. Okay, for both of them, the labels is a 10-dimensional vector because it's a multi-class problem, right? So given an xi, you have a yi, right? This yi can belong to 0, 1, 2, any of the 9 values. And this I can represent it as a vector of size 10, 0, 1, 2, so on, so forth, 9. And if yi equals to 3, I'll set this to 1, rest everything to 0. Right? So this is one hot encoding of the class label itself. Okay, and since we have a multi-class classification with 10 classes, what is the equivalent of logistic regression in this case? We have seen Softmax Classifier, right, in one of the previous videos. So we will use a Softmax Classifier, which is basically a generalization of logistic regression to a multi-class setting. Okay, so we have 55,000 training data points and 10,000 test data points. Now let's import TensorFlow. Okay, import TensorFlow as TF. Very, very simple. Okay, first I want to check whether I have GPUs or CPUs and what can I use in my system. Okay, so I'll say from tensorflow.python.client import device library. So it gives me, it's basically saying, and if I say device lib.list local devices, on my Mac, this is the result that it gave. It says that I have a CPU, right? I have a CPU with some memory and things like that. But if I had a GPU, I have a desktop also at my home, where I got an output like this, where it says I have two devices. My first device is a CPU, my second device is a GPU, and this GPU is GTX 1070, right? So if you have two devices, you can choose to use GPU. Since I have only one device, I'll just say by default it will use only CPU, right? But if you have a GPU, this is one way for you to test if you have a GPU or not in TensorFlow. And if TensorFlow can actually work with the GPU or not. If TensorFlow gives you this output, right, when you give device underscore lib.list local devices, if it gives you this output, your TensorFlow is perfectly connected to your GPU and you can use the GPU for your processing. Anyway, you have Google Colab, right? You have Google Colab for processing your work if you don't have a high-end GPU. So don't worry about it. And this whole example, you can run it on CPU. You require a little bit of patience because I ran it on my laptop and it took a while to run, but it ran eventually. So all the examples that we're showing you, right, can be run on a CPU. Don't worry about it. So you can either run it on a CPU, even if you don't have a GPU. If you have a GPU, great, run it on your GPU. If you don't have a GPU, run it on your CPU or run it on Google Colab. That's my strong recommendation. Okay. Okay. Now let's look at something called placeholders and variables. Okay. So the general rule of TensorFlow is as follows. In TensorFlow, you have three types. I mean, at a very low level, there are more, of course. You have constants, you have variables, and you have placeholders. Okay, let me explain what is the constants. We know these are like constants in Python. These are like variables in Python. Placeholders is a different thing. So, for example, suppose if I'm training a Softmax, okay, I have weights, right? I have weights, and I have my biases, because here my model is W transpose X plus B. The sigmoid of W transpose X plus B equals to my Y. Okay, so this is the model. So there is a bias term in addition. So your weights and biases are the parameters. Okay, in a lot of examples, I don't focus too much on the biases, but you can have them. So your weights and biases are variables, right, which need to be updated every time. That's why it's called a variable. A constant cannot be updated. You cannot update, you cannot change a constant. Right? While a variable is something that you can update and change. On the other hand, a placeholder intuitively speaking, is like a memory location for which you define maybe you define the size sometimes you don't even define the size. But a placeholder is typically used as follows. Okay, imagine you're training a mini batch. Suppose you're training a mini batch, okay, of let's say 100 xis. Okay, so when you're training a mini batch of 100 xis, you want to store these 100 xis with x1 here, x2 here, x3 here, so on and so forth, x100 here. You want some memory in which you want to store these 100 values. Since it's mini batch, you will use these 100 values to do one iteration, right? So you want to do one iteration with these 100 randomly chosen values of xis, and after this iteration is over, these 100 values will be changed. So a placeholder is typically stored. A placeholder is typically defined to store these transient things like mini batches. You can think of them as memory that is allocated for your task with no values to start with. So when you define a placeholder, you sometimes even don't define exact size, which means it's like a placeholder where you will eventually put some data. When you actually are performing your stochastic gradient descent or Adam optimizer or any of those optimizers, you will fill this placeholder with values, with different values for every iteration of mini batch. So placeholders can be thought of as a modified form of variables which are used in TensorFlow for the case of data points, typically data points. Okay, so we'll see some examples here that will make it better for you. So here I'm defining, so in this line, I'm defining a TensorFlow placeholder, right? I'm defining a placeholder here, and I'm saying the placeholder has two parameters. Okay, the placeholder is of type 32-bit float values. And here I'm saying that one dimension, so it has two dimensions, right? This placeholder has two dimensions. I'm saying one dimension is 784, the other dimension is none. Whenever I say none, it means I don't know what it will be, right? I don't know what it will be. It can be any number that I choose. So this is like a placeholder. In other words, I'm just defining what the type of data or what is a tensor. So this is a 2D tensor, right? Because a matrix is a 2D tensor. So what I'm doing here is I'm saying X is a placeholder which can hold 32-bit floating point values, right, of size 784 dimensions, but the number of points is still not known to me. I will do it. I'll set the number of points when I need to. Right now, I'm just defining its type. Defining its type, I'm defining one of the dimensions. I'm not defining anything about the second dimension. And it's typically used to put data here, your x's. Okay, so that's one. The next thing is you need a variable. So here I'm defining my variable called w. Okay, so w is of type what? So for every w, look at like this. Look at a unit like this. Look at your sigmoid units, right? What do you get here? You get all the inputs here. So your w is here, your x is here. Your x needs to multiply with w, right? So you have your 784 dimensions for each weight, and you have 10 classes here. So your total weights, because you have a softmax, right? Because you have a softmax, how many weights do you have in this softmax? Let's look it up. Okay, suppose you have your inputs here. Sorry, let me change the color. Suppose you have your inputs here. Your input dimension is 784, and you have a sigma, and you have your softmax here. You have softmax, and you have to get a 10 outputs out of this, right? Output 0, 1, 2, so on, output 9. 10 outputs. So how many connections are here? 784 cross 10. And those many weights are what you have here. And that's what we are defining here literally. I'm saying my W variable, my W is a TensorFlow variable, which I'm initializing to zeros. I'm initializing everything to 0. Okay. Where I have 784 weights cross 10. 784 cross 10. I have 784 because all these weights, every input now is connected to each of the 10 softmax units, right? The next one is also connected to all the 10 of them. The third one is also connected to all the 10 of them. So I have 784 into 10. Similarly, I have a bias term, okay? And I have one bias term for each of my units. So if this is my input and if this is my softmax, right? Suppose I have my inputs here. So what's happening is all of these are connected here to this softmax unit. There are 10 such softmax units here. And there is a bias term. There is a bias term for this input. Okay, so these are my inputs. I have weights here, 784 weights here, and I have a bias term. Bias just behaves like a weight. As we have seen in the linear regression, logistic regression chapter, bias is just, even if you ignore it, it's okay. The world is not going to collapse. Okay, but let's have it for completeness. So I'm defining two variables and I'm initializing both the variables to 0. I have a W and B. Now I'll define what Y should be. Okay, I'm saying my Y is, first I'm multiplying X and W. So tf.matmul, which basically means matrix multiplication. So you multiply W and X and you add B to it, right? So this is what you get. You've done W transpose X plus B here. And on top of it, I have to apply a softmax unit, because what is my model? My model is literally that I have my xi's here. I do W transpose xi and I apply a softmax on it. Isn't it? And that's what I'm defining here. I'm saying my Y is tf.nn.softmax, matrix multiplication of X and W plus B. Here I'm defining how to compute Y. Here, given X, I am defining how to compute Y. Since we are using a softmax classifier, this is a very simple definition, right? Now, so these are your Y's, right? This is the definition of Y. Now the true labels, so given each xi, right? We have defined how to compute yi here. This yi here is supposed to be y hat actually. This is yi hat actually. There is an actual yi, right, which we are calling as y underscore here, or y actual. Okay, so for every input xi, there is a y actual, right, for which also we are defining a placeholder, and this placeholder is again float of size 10, right? So for each xi, for each mini batch of xi's, let's say x1, this is a mini batch, x2, x3, right, so on and so forth, x100. Let's assume I have a mini batch of 100. Corresponding to it, I'll also have a mini batch of the yi's, the actual yi's corresponding to all of them. So all the actual yi's, we are calling it in this code as y underscore. The predicted yi's, we are calling it as y. Okay, don't forget that notation. Here we have tried to use the example that is there in TensorFlow so that you understand it easily going forward. Now comes the fun part. Now I want to define what is the error. Here we are just defining, we have not run anything, we are just defining stuff here. right? Next comes the very, very important thing. Now I want to say, what is my cross entropy error? Define cross entropy error. Cross entropy error is defined as, okay, let's see. It is the mean of sum of y underscore. What is y underscore here? Y underscore is actual y. Y underscore is nothing but yi, the actual label. TF of log of y. Y is predicted value, because we defined y earlier in one of the previous lines, right? So what does it say? It says log of yi hat, because y underscore means the true yi. Y here means the predicted value. So what I'm saying here, I'm saying take yi log yi hat, sum it up, and take the average value. Okay, this is the meaning of cross entropy, right? This is basically your log loss. Cross entropy is nothing but it's a generalization of log loss to multi-class setting. Here you may wonder, what does reduce sum? See, it doesn't say mean, it says reduce mean. It doesn't say sum, it says reduce sum. You may wonder, what does reduce sum mean? So there's a very nice tutorial that we have pointed a link to. Reduce operation in a nutshell. I'll show you what a reduce operation is. Okay. So here is a nice URL that we have pointed to. Let me just open it up for you. Okay. So reduce operation works like this. Okay. Very, very nice example. In a nutshell, a reduce operation takes a tensor as input, and it returns another tensor as output by performing some operation. So it is reducing the number of dimensions of the input tensor to generate an output tensor. So let me explain you this with an example that will make it concrete. Suppose I'm creating a constant here. I'm creating a matrix here. What is this matrix? 1, 3, 2, 0, 0, 1. Okay, this is my matrix A. First line. Second line, I'm saying TF dot reduce sum A. So when I say reduce underscore sum A, what it does here is reduction basically means this is a 3 rows and 2 columns matrix. Reduce this dimensionality, and it's a 2-dimensional tensor. It's a 2D tensor, right? Reduction basically means that I'm trying to convert a 2D tensor into a 1D tensor. Okay, so when I say reduce underscore sum A, what it does is it takes the sum of all the elements that are there in the matrix. Okay, when I say reduce underscore sum A, it says takes the first value, sum set 1 plus 3, it does 1 plus 3 plus 2 plus 0 plus 0 plus 1, which is equal to 7. So 7, you can think of it as just one value. So this you can think of it as 1D tensor, right? Because what is a 1D tensor? A 1D tensor is basically an array. This is an array of 1 cross 1 element. Right? So reduce sum literally has summed up all the elements and reduced the original array A into a new array called B. Right? Original tensor A into a new tensor B. It has reduced it from a 2-dimensional tensor to a 1-dimensional tensor. Okay, this is what reduce sum does. Okay, now let's see what other stuff we have available. The second one is called reduce sum A comma 0. Okay, so when you say reduce sum A comma 0, what it does here is, okay, when you say A comma 0, okay, what it does is it does a column wise sum. So reduce sum, I'll just write it as RS. Reduce sum A comma 0, what it does initially is it simply sums it by each column. So it returns 3 comma 4, which is again a 1D tensor. Remember, this is a 1D tensor of size 1 row cross 2 columns. So because you gave it 0, what it's doing is it's doing column sum. If you gave it 1, if you said reduce sum A comma 1, okay, it would do not a column sum but a row sum. Okay, and what does the row sum look like? The row sum looks like 4, 2, 1, which is a 3 cross 1 1-dimensional tensor. So if you said reduce sum A comma 0, it's doing a column sum. If you're doing reduce sum A comma 1, it's doing a row based sum. So it's doing this row sum when you say A comma 1, right? So this is a reduction operation. So in reduction, you have reduce sum, you have lots of reducers. You have reduce mean, right? Reduce mean basically sums up everything and divides it by the by the average value, by the number of elements so as to get the mean value. So reduction is a very, very nice, simple operation which is used a lot in TensorFlow, right? So literally look at what we are doing here. We are saying, okay, let me just take this a little here. Yes. So the first step we are saying is take your yi's, take log of yi hats, multiply both of them, and perform a reduce sum on the reduction indices of 1. Okay, remember your y hat is an array. Your y is also an array. Your y underscore is a binary array. Your y here, your y underscore is nothing but y, your actual y's. Your y here, your yi's. This is yi hats. These are probability scores. All these are vectors. You're multiplying vectors and you're doing reduction so as to compute sum and then mean. That's what your cross entropy is, right? Cross entropy is the average log loss, isn't it? That's why we have just defined our cross entropy here. Next step, I want to define how do I want to train. Okay, so the step here is I'm saying that my train step basically means that tf.train.gradient descent optimizer. What I have here is the learning rate. So I'm saying my training needs to be done using gradient descent optimizer, which minimizes cross entropy. I've defined cross entropy here. I've defined what cross entropy here is. I've defined my loss function here. And I'm saying my training needs to happen using gradient descent optimizer with this learning rate, and which minimizes my cross entropy. Sometimes getting a hang over the syntax of TensorFlow takes time. As I told you, the first time I learned TensorFlow, it took me almost 2 months to become comfortable with TensorFlow and to be able to write code without going and checking on Stack Overflow. It took me some time to get comfortable with TensorFlow, frankly speaking. So it's a slightly tricky notation that you have to get used to. But there is a lot of help available online. Initially, what I did for the 2 months was I copy pasted code, played around, tweaked it a little till the time I got a hang over it. Okay. So if you want to understand the gradient descent optimizer, we have a link here, so which I'll go to right now. You have all these optimizers. You have your gradient descent optimizer, ADA delta, ADA grad, right? You have your SGD with momentum. You have your Adam. There are others also. You have your RMS prop here. There are other variations and more algorithms that are available in TensorFlow, right? So, but all the major algorithms that we have learned are available here. That's why I waited for the code a while, so that once you understand the theory, it's easier to grasp this, right? And what it does here is basically simple gradient descent. Now, once I've defined my gradient descent, now I'll go into the core crux of the thing. First, I'll define a session. When you define a session, what it says is TensorFlow sessions. You can just say interactive session or just session. Okay, so session is basically like you're starting the computation from here. You're defining the starting of computation from here. So when you say session, what it's doing is it says, okay, at the end of the day, TensorFlow converts everything into a computational graph. Recall what we discussed about computational graph, right? When I showed you a bunch of examples, a computational graph in a nutshell is all about, okay, I have my input x1 here, I have my input x2 here, both of them need to be added, and then I need to multiply with, let's say, b, right? And then I have to apply a sigmoid operation on top of it to generate y, something like that. Okay, so this is a computational graph, and it goes from left to right. First, it needs to have x1 available and x2 available. Then it will execute this. Once this is executed, it will take b here and perform a multiplication operation. And then once everything is available here, it performs a sigmoid operation, etc., etc., etc. I've just drawn a dummy computational graph here. So once you start saying that session, when you start defining your session, you're saying from here on, I'm defining the core thing that needs to be run. Till now, what I've done is I've just defined all the stuff that I care. I've defined my variables, I've defined my placeholders, I've defined my laws, I've defined what optimization I want, but now I'll start running it. From now, when you say session, start the session. Okay, this is the actual session where the computational graph is created and will start to train, right? First step I'm saying here is initialize all the global variables. Global variables initializer.run. This will initialize all the variables, your W's, your B's, all of them to zeros. That's what you have initialized them to, right? Then in this step, I define what I want. In this step, this is the fun part here. Here, what I'm saying here is, I'm saying I want to run a loop 1,000 times. and I'm creating a mini batch. Okay, here look at this, mnist.train.next batch 100. What this returns me is, it returns me a mini batch of 100 xis and yis, which I'm calling it as batch xs and batch ys. Okay, and I'm running this loop 1,000 times. Okay, I'm running this whole loop 1,000 times, but I'm literally doing a mini batch SGD here. I'm literally doing a mini batch SGD. I'm creating a batch of size 100 units, and the next batch will give me new batch every time. Okay, and I'm storing all of that in batch underscore xs and batch underscore ys. And in the session.run, I'm saying run the training step. What is training step here? Just look at it. When I say training step is basically the train step defines what is the optimizer and what is the loss, right? So in this step, what I'm saying here, once you get your mini batch, then run your optimizer, which minimizes cross entropy. Okay, and you feed it. You feed your xs as batch xs, your y hat or y underscores as your batch ys. So here you've created the mini batch, and now you're feeding the mini batch. You're feeding the mini batch into your training algorithm, and this loop keeps repeating. And at the end of it, what have you done? You've done 1,000 iterations, with each iteration being 100 times, 100, which with each iteration having a batch size of 100. That's what you've done here. Once you've done all of this, now what will you do? You've run all of it, you've got all of it. Now you want to see how accurate you are. So I am saying tf.argmax y comma 1, because here y is my y hat. This y is the true y. Okay, suppose if given an xi, let's assume given an xi, okay, suppose it predicts that my class label is, let's say 0, 1, let's assume my class label is actually 2, rest everything is 0. Okay, so I'm taking the maximum value here. I'm taking the maximum value of y underscore, which says 2. Similarly, in my probabilities that I get, because what softmax returns you probabilities, right? 0.1, 0.2, 0.7, etc. It says find the maximum probability, argmax, find the maximum probability amongst your y hats. Suppose if this is 2 and this is also 2, it returns the same value, then you call it as correct prediction, or else you call it as wrong prediction. Right? Once you get correct predictions, you're computing the mean of correct predictions now to get the accuracy. And this simple code that we have seen gives you 89.98% accuracy. That's it. It's very, very simple. It gives you 89.98% accuracy. We haven't even run like proper epochs, etc. I'll show you the code in a while. Okay. This is some code that we have written just to plot loss, train loss, test loss. But whatever we have learned till now, we have put it in a single cell right now. Okay. Whatever we have learned. So here what we are saying here is, I want to train 15 epochs, which a batch size of 1,000. See, whatever we have seen earlier, now we are trying to put all of that into a single place. Right? And I'm defining my cross entropy as the mean of softmax. See, you can also get softmax cross entropy with logits. Okay? And I'm defining my training step as gradient descent optimizer, which minimizes cross entropy with a learning rate of 0.05. Okay, now I'll run it per epoch. This whole code is basically a repetition of what we have seen with epochs put in place. Remember, what is an epoch? An epoch is when all of the training points have been seen have been passed through once through mini batch, right? So same code, everything same. I'm just plotting it here. So if you see the plot here, this is my softmax cross entropy loss or log loss, to put it bluntly. Okay, my blue line here is the training loss. My red line here is the test loss. Okay, and this is my epoch. This is a very, very important plot to have. Okay, so my x-axis is epoch, as you'll notice as I'm sending more data, as I'm iterating, as my epoch number is increasing, both my train loss and test loss are reducing. And we've only run it for 15 epochs. But even after this, if you notice here, even after this, they're reducing. Even if I stop it at 15 epochs, my training accuracy, my test accuracy is 90.36, which is a very healthy number. My test accuracy is 90.36. What you see here is the log loss or cross entropy loss. Since it is reducing, ideally, even though I stopped this at 15 epochs, you can keep running it, and you should keep running it till the time. So this is my loss. Right? This is my training loss like this at 15, and this is how my test loss looks right? At 15, it looks like this. So I'll keep running it. I should ideally keep running it. It will reduce further. It will reduce further. Once it plateaus, somewhere it will plateau. Somewhere it will not change much. Maybe this is 100 epochs. Stop here. Once it doesn't reduce anymore, stop here. And whatever model you get. So this is your epochs. This is your epochs. This is your cross entropy loss. Okay. We have only run it till 15, but you can run it further. And to run it further, it's very, very simple. Very, very simple. You just change training epochs equal to 100 or maybe 200. Right? Very, very importantly, TensorFlow code can get very, very confusing if you're a newbie. If you're just getting started, as I told you, I took 2 months to get a hang of TensorFlow code. It's very, very different from traditional code that we typically do in Python or scikit-learn. So it's new. It was new even for me. So don't worry about it. You will learn TensorFlow by reading others' code. Like there is a lot of brilliant code that you can get from TensorFlow documentation. Okay, you should read lots of other people's code and also go through some of the tutorials that we have shared with you. Okay, not just the tutorials that we teach you, but others also. So while this notation might seem too confusing at the start, eventually you'll get used to it. Okay, it requires practice. It just requires practice. There are two types of practice. One, read others' code and write your own code. These are the two things that you have to do to actually become comfortable in programming, especially in a new environment like TensorFlow. We'll also see Keras at the end of this chapter, which is much more easy. Keras is much more simple. You don't have all this complexity. Keras will feel more like scikit-learn. But TensorFlow is also important to learn because there's a lot of nice code that you want to read and learn. You may write very little TensorFlow code at the end of the day, but being able to read others' code is a very, very important skill.